Okay. But anyway, this were discussed also before, so you not miss. So let me rephrase this question again. What is the analog or generalization of complex conjugation uh, for Hilbert spaces? What do you think? So we want to imitate this for an element of Hilbert space. Dual space. Okay, good. Okay, okay. So let's try. Is dual space is going to do this work? Okay. So suggestion: dual space. Now, what is so? Okay, and how do we define dual space? So we take an element in some other space. So let's call it the dual space. So by dual, you means functionals, right? Or what do you mean by dual space? Yes, yeah, functionals. Okay. And then you have some element, let's call it phi, and then you act phi on u. And this is a number, C number. So according to your suggestion, we should consider phi as a complex conjugation of u. Am I right? Exactly. Okay, very good idea. So now let's check. Say this is true. Okay. So say this is complex conjugation. Uh, right. So this is our working definition. Um, this is complex conjugation of u. Okay, good. So now, as a special case, if we go to finite dimensional situation, then we should reproduce what's written here, right? So now let's check. Can we reproduce that? And even before checking directly, just recall to all of you that this phi is C-linear. But is this action C-linear? C-linear means linear for with complex number, okay? So, so that means if you have a element here and if you have element in complex, then you see that the linearity changes with complex numbers, not on the real part. However, for phi, does it happen? Or in other words, if you put u equals to this guy, from this definition, do you get phi equals to this guy? Is it clear whether we get or not? Because that's really crucial. So feel free if it's not clear. No one or are everyone lost? Like what's going on? Okay, let's go step by step so that if we of any of us are lost. So if you put u equals to this, so put u equals to this, and then let's put this equals to this, and let's compute. It's not a hard task. So if we multiply z, okay, zcc, sorry, I use consistent notation, cc. So zcc and z, this belongs to real, isn't it? Yes. But this gives us in complex. And the reason is, in this structure, we don't have anything which makes this operation, right? Remember how this was defined. Let's go back. It was defined by continuity here. So how is defined? You take an element, okay, and you say that the condition is that continuity. And continuity means that if you have this absolute value that is bounded by derivative of your test function. So in the whole process, is there anything which mimic the complex conjugation structure? Answer is no. So is it clear to everyone why the answer is no? Take your time, don't be stressed, but try to clarify. It's not just some abstract definition and proposition and theorems, rather why some things are like that. Okay, so we also wanted to, we just don't want to know how the game is played, but we also want to know why this game is played this way. So is this clear to everyone that if we use this as our working definition, then we cannot reproduce this? Is it clear? Okay, so thank you. Only two of you of us have replied. Hopefully others are in front of a screen, and if you are not, okay, then yeah, then it's up to you. But if you are, it will be really useful if you please participate. Because yeah, unless you tell, it's an online thing, I cannot see any of you. So this is only your response that I can see or understand. Okay, that means that the dual space is not going to do the job. So this is not this. Okay, but it was really a good suggestion, and you were very close actually. So now hint for all of you: what we discuss in the first lecture has something that mimics this structure. Could any of us tell what was this structure? So, what we discussed in the first lecture? So, we start our lecture with something called inner product space. And what does an inner product do? So, you take an element here, you put something there, and then this gives you, in general, a complex number. But if both are same, Sorry, I wanted to write this way. So u v is a complex number, but u, maybe I want to highlight this. So u is a real number. Do all of us remember this thing? Because this is basically norm square. So it's a real number. Okay. Now, can you see some similarity with these two guys? Okay, yes. So, and what's the similarity? Is that if you consider u in the second slot as z, then the other u in the first slot behaves like z complex conjugation. Is this clear to all of us? Thank you. So apparently only two are responding. What about the others? Are you lost? Or I mean, if you are not in front of the screen, then it's okay. But are you lost? So who is lost? Please feel free to write me a personal message. Okay, thank you. So it seems that we have understood. Okay, then what's the upshot? How should we define complex conjugation or a generalization of complex conjugation for Hilbert spaces? The answer is with. Can any of us write in chat what should be this structure? Feel free, even if it is not right, we are going to see why it's not right, and hopefully we can get what is right. So don't be afraid. Like there was a nice suggestion at the beginning that dual is the notion, and then we checked and apparently it didn't work, and that's perfectly okay. That's how science works. So what is the generalization? So this similarity tells that what is the relevant or analog for complex conjugation for Hilbert spaces? Can you see? Exactly. So this is precisely the inner product that gives you the complex conjugation. Okay, good. So we have inner product, and now let's go back. So since we have inner product, can we, okay, so now first part is solved. We know how to take complex conjugation. Okay, so we just use inner product. Next, what we have to do, we have to change rows and columns. Can this be done? And as one of you have written, because it's infinite dimension, we never know what is the all of the rows and columns are not known to us at all. So we cannot do this operation at all. This can be done in this sense, okay, but this cannot be done. And that's why you cannot imitate this idea to define adjoint for an operator on Hilbert space. So is this clear to all of us? Because this is really the heart, why we need to define something in a different way than we know in linear algebra, okay? So before defining something, we first need to know why the existing definition doesn't work. So is it clear? Okay, thank you. And if not, please raise your voice because that's really crucial. Okay, so let me send back this then here because maybe they are more relevant. Okay, I put it there. In a box. Okay, good. So now I think we all have understood, at least you have responded, that we cannot just imitate linear algebra. And this was the question, like, can we see why in quantum mechanics we need this mathematical sophistication? I hope now you can start. I mean, we have given an example before, but hopefully now you see another instant. If you try, you cannot use linear algebra. Just you cannot. Okay? Okay, so now let's go back to our definition. We do not need. Okay. So now question is, what is the right way or what is the right generalization of this idea? And the idea is that, okay, you take a linear operator from Hilbert space H to Hilbert space K, and then you have to mimic somehow this exchanging rows and columns and then complex conjugation, both simultaneously. Now, remember, this is an unbounded operator. So we have to sure that we are not going beyond our domain. So, and also we have discussed it and explained to you that an operator means a map and a domain. So first, let's define the domain of this map. So we see that this should be in the other. So this is element of this space. And now what we want. So had it been a bounded operator, what we can do, like the matrix case, we just put this in the other side. Right? So maybe I write it here. So maybe red. So that it's like a red light. W T star V. And compare with this. Now, what's the problem of writing this thing? Why this is problematic? This is problematic because we do not know this domain yet. And if we do not know the domain, then how can we define an operator? However, we understand what the structure is required. So what is required? This has to be something which has this property, isn't it? Like W and then some element so that the inner product of W gives this, because that's our mental picture. We want to define this equals to that, right? But since unboundedness is the issue here, we do not know it yet. We say that, okay, there exists some element. That's why there exists some element. Okay, that's how the definition actually came. So maybe it looks a bit abstract at the beginning, but I hope now it's clear why we need this abstractness and how it mimics what we know in linear algebra. Okay, before I go again, any question? Why, how, and what does this adjoint mean? Although we are going to do several examples, so you see concretely, but for the time being, what the terminology means, at least the philosophy, why we need to do this and what it tells. Is it clear to everyone? I mean, I am asking it every step because this is really one of the heart, this unbounded self-adjoint operator. And this is super, super, super central in quantum mechanics. So if you miss something here, you will miss in quantum mechanics part. All right, so thank you for your response. And now we say, I hope now it's clear why we want to set this thing. So we said, okay, T star V is precisely the element U, and then the T star is called adjoint of T. Okay, now we consider a Hilbert operator on a Hilbert space only because we want to consider self-adjointness. Okay. Someone mentioned it before and noticed it before that I made this mistake earlier, but thanks again for that. Okay, so what is called a self-adjoint operator. So before going self-adjointness, first we take a small step. So an operator is called symmetric if T and if T star is an extension of T. Okay, so what does this mean? This means that the domain of T star may or may not equals to T, but it is always larger or equals. Okay, so if I want to give you, yeah, so there is already this picture. So the picture is like this red one or blue one, the one you want to say. So the domain must be, or I mean, okay, you can actually prove it, but I'm not going to prove it, that this is at least bigger or equal. Okay. So since this is bigger, this may be bigger, that means at this point we do not know whether the equality is attained or not. And that is called symmetric operator, unfortunately. Sometimes this is called self-adjoint in physics textbook. Okay, which is definitely not true. So what is relevant to physics? I hope you see very concretely what is relevance to physics. And now we come back again. We say that self-adjointness is thing that, okay, we extend the domain. Like, see, this is like this part and this is the bigger part. So what we can do, we extend the domain. So maybe I draw instead of a blue one. Yeah. So maybe I first draw an intermediate one. Two, 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 two. Okay. So now I extended it, but this extension still is not equals to T star. So what you do? You extend more. Any questions? Sorry. No? Okay. So I give another step. So now we are extended more. Okay, so the dotted one. But still it's not equal. So we have to extend even more. And then this is called self-adjoint. Okay. So I hope at the beginning there was the real this question, and it should be like why we are considering about domain. Without domain, we cannot define self-adjoint operator. It's just not possible. It's not mathematical sophistication or mathematical jargon. Okay, it's simply not possible. Okay, and then another notion that we will see is something called essential self-adjoint, which means that if the closure, we know what is closure, is itself self-adjoint. In fact, we see that some of the interesting quantum mechanical observables are essentially self-adjoint. Okay, so before now I go for examples. Any questions about these terminologies, what it mean and what it or which way it differs from before? Please feel free to raise your voice, because it is really the discussion that will increase your understanding, that will increase. If you repeat upper part, that T belongs to HK part. No, so from here T is only an Hilbert space, an operator on H, because we want to have this condition, right? So if in a different space, how can we have this condition? So this is only here now. Okay, maybe I make a gap so that is even visible. Mm, clear now? Ah, you mean the here? There? You mean this part? This part? Okay. Yeah, yeah, sure. Okay, so we want to define adjoint. Okay, so and how we define adjoint. So again, let's go our friend in linear algebra. So the moral, or say the mental image we have, we change rows to columns and we do complex conjugation. So we have discussed about complex conjugation, which is by the inner product. Good. And now this rows to column, which means that, okay, if so by changing rows and columns, what does mean? That before it was acting on some row and now it acting with some column, right? Okay, so now we want to imitate the same thing. So morally, we want to define something like this. So T acting on W equals to V, and then the adjoint should act on V is same as W acting on T star V. Okay, so that's what we wanted to do. Okay, what's the problem? Why we cannot write it? The reason is the domain issue. Had it been a bounded operator, maybe I write here. Uh, if it is bounded operator, then we can write it bounded. Okay, why? Because bounded operator is defined on whole Hilbert space. So if T acts on W, still this is in the Hilbert space. It's not going anywhere else. But since this is unbounded operator, we do not know where is TW, right? We do not know. But we know this is somewhere in K, but not in a, remember, is we do not know what is the range of TW. We know that just this is an element in K, okay? Then what we do, we take in our product because it's in K, and now we want to mimic this structure. So what this tells that the adjoint of this operator T, if acts on V, then this should give exactly the same thing if that object acting on W is equals to this. And that is what is written here. Okay. Now, now we can say, okay, T star V is the U. Why not the other way around? Because we could do for bounded operator. So this route is okay for bounded operator because we know that T star V, because we know that TW is in the whole Hilbert space. We also know that this is also in the whole Hilbert space. We know what is the range, what is going. But in this case, we didn't know at priori where is TWV. So what we do, we play the other way around. We say that, okay, we do not know, but we know at least that the adjoint acting on something, some element of K, will be an element of H, of course. And that element, inner product with W, must be close to that. That's property we know. Once we know that, then we say, aha, this is precisely what we are looking at. Is it clear now? If not, please do not hesitate, because that's really central and one of the important parts. Yeah, thanks. All right, so any other questions about self-adjoint operators and why we have defined? And this sometimes heuristically people say, oh, in maths you just make it complicated. This is not required. I hope, I mean, if it's not clear, still raise your voice. But you see that without this thing, there is, I mean, I don't see how can you even define self-adjointness. How can you do it? Forget about precision and sophistication. Okay, so if there is no question, then it's time to go for examples. Before examples, I wanted to ask one thing. Since I couldn't take this last lecture, how can we compensate? So, um, for instance, mm, so the next tutorial is on 7th of June. Um, One thing be done is that instead of that tutorial, I take one lecture, and the next day, 8th of June, we can shift the tutorial. So that can be one option. I want to shift the tutorial instead of lecture, because then we can just continue the spectral theorem part. Okay, otherwise there is a break. So that's why I propose. So that's one proposal. Or we can just add, we just keep going, and then we add one more. So instead of 5th of July, our last lecture will be 6th of July, which hopefully, let me check. Okay, so 6th of July is actually Monday. So that's actually a bit problem. Mm, okay, so let me ask. How about um, shifting the tutorial from 7th of June to 8th of June? Oh, I see. Thanks a lot. That is also Monday. Mm, okay. I see. It's quite packed. Mhm. Uh, is that okay if I take maybe, okay, that's maybe too much, but okay, let me ask anyway. Yeah, that I was going to ask, like, maybe I just continue. So usually our lectures are 2 hours. So maybe I take two lecture for 3 hours with maybe 15 minutes break, if that okay. So then, if I take 2 hour, two lecture with 1 hour extras, and then okay. So is there anyone is not fine? I can see 11 participants. So only two of you have responded. So please, at least for this, everyone respond, because that's really organizational. Um, could you please respond? Okay, two. Okay, three. Others, please, if you are in front of a screen, please respond. Okay, four. But we have, okay, if you exclude me, then we have even six more. So what about others? Are you not in front of screen? Okay, thank you all of you who responded. Maybe others are not in front of screen. So I can write in the Slack group. But thanks all of you the 4 person who responded. All right. So then something concrete. We want to complete examples. Yeah. So the first example, yeah, that's what I had initially in mind. I wanted to actually describe the matrix thing later. That was my initial plan, but when I was preparing, it came to my mind, probably it's better to if we discuss. So the matrix part, I hope now is clear to all of you. If not, as I said, feel free to raise your voice. Now go to the next example that we also explained, but it's never a bad idea to re-explain again. So I think one of the interesting operator we have learned so far is the multiplication operator. And now we consider f is a complex valued function, and we consider multiplication operator. We know what is the domain, how to define it. And now if we consider this is a bounded guy, then we know we can just use this strategy, right? Because I mean, this is strategy, not exactly this thing, because we do not know the number of columns, but we can just write this explicitly. Maybe I write it. Oh, it's written already. So we can now do it if it is a bounded situation. Okay. All right. And then you see that the adjoint of multiplication operator is the complex conjugation. Although I was using this CC notation before, but this is in maths more or less standard to use bar for complex conjugation, which I shall use from now. All right, so that was more and less what we discussed, but I tried to elaborate a bit. So if you do not have any question, then let's delve into some other examples. So beginning of the lecture, one of the things we try to motivate or use as our motivation is some of the fundamental equation in physics. For instance, heat equation, wave equation, Schrödinger equation. And we have seen that all of these equations are differential equation. That means that differential equation is something is pretty important in physics and also other areas, for instance, in economics and of course in pure maths. So maybe it's not a bad idea to consider differential operators. So let me go in the world of differential operators. So before going there, let me introduce some terminologies which may or may not be known. I mean, if you are familiar with real analysis, then you are familiar, but let's keep everyone on the same footing. So a function f is a function from an interval a to b, and here interval, I mean that this is something real, okay? Okay, this is called absolutely continuous. Oh, sorry, I forgot. Are absolutely continuous if and only if there exists a function f which is L1. I hope now all of you are comfortable with these notations, such that for all x in the interval a b, the fundamental theorem of calculus is true, which means that f of x equal to f of a plus integration from a to x g of t dt. Okay. Okay. We denote the set of all such functions as AC. Yeah, AC for absolute continuous. And in which interval to indicate B. So this is set of all such functions. Good. And in this setting, this function g is called, as you know, the derivative. So maybe I write once. If f is an absolutely continuous function in the interval a b, then f is definitely continuous and this is almost everywhere differentiable. So those who are not familiar with this notion of almost everywhere, this is somehow related to mostly related to measure theory. Loosely speaking, the notion is that okay, it's differentiable except something, yeah, almost everywhere, but there are some points except those. So let's not go there. This is again this real analysis thing, which is important, but okay. With f of x prime. So here, yeah, I haven't used prime. Prime means derivative equals to g of x almost everywhere on the interval. And of course, we call g is the derivative of f. Now we define two sets. The reason is that we'll see that this set will be used as domain of some interesting or not interesting differential operator. So first one is H1 interval AB is defined as the almost continuous functions on AB such that the derivative of f, which we know what is that, is L2 over the interval. And now we define another functional space called H2 AB, which is set of differentiable functions on the interval such that the derivative is now on H1. Okay, so we define these two spaces. Now we do integration by parts. So integration by parts. And what does it say? So f g. So this is the L2 product. Maybe I write L2 plus integration parts, you know, the other way around. So f g prime. So all are L2. Okay, so okay, better write. Otherwise, it might be confusing. So this is equals to, as you know, f g bar a b, which is nothing but, sorry, f of b g of b minus f of a g of a. I think I made this comment before. Some people use complex conjugation in the second um, uh, place in this inner product. Then instead of bar here, you will have a bar there. Okay. Doesn't matter. So it's a matter of convention. Okay. Um, we also compute for the time being the second integration by parts for the um, second derivative. Okay, I wanted to also keep in track. So here, this is for H1. Maybe I should write somewhere. Okay, I can write here. Okay, so now, because we have two spaces, so let us keep in track. If G belongs to H1 AB, then this equals to this equals to this. Okay, good. Now we consider the other space. For all Fg in H2 AB, so if double derivative of G L2 minus f double derivative of G L2 and integration by parts, this gives first derivative of f complex conjugation of G minus complex conjugation of f first derivative of G from A to B, and this gives us nothing but first derivative of f at B, its complex conjugation, and then G of B minus first derivative of f of B complex conjugation. It's without derivative. Now first derivative of G of B minus first derivative of f of A, G of A. I don't want to go next line, so I keep it here. Minus minus make it plus f of A complex conjugation first derivative of G of A. Okay, so very trivial thing. I hope you have seen, but just to warm up. Yeah. Okay. Now go to example. So now we consider T domain. Okay, I mean, we can just write. So remember what's our purpose? What we I mean, now I think is also a bit intuitive. We want to consider differential or differentiation. So we cook up these spaces. And now we consider first the first derivative. So let T be an operator from the domain H1 naught. So we have defined H1, not H1 naught, but I'm defined shortly. AB to L2 mm, mm, mm. Okay, better. Okay, no problem. We didn't define here. Okay, so how is defined? So you take an element U and T of U is given by minus I times Right, put it. So this is matter of convention. Um, I will use minus I, first derivative of u. And question is, what is this space? So what is this not is doing? So this is u on h1 ab as you expected, and then additional thing is that at boundary they vanish. So ua equals to 0 equals to ub. That's the not. Okay. Uh, this look analogous to a differential equation operator, right? Uh, what do you mean by differential equation operator? Can you write a bit or tell? You mean that like Laplace equation, heat equation, something like that? Ah, okay, okay. So, okay, there is a question that there is this notion about this first order differential equation, and we use self-adjointness of that. Yes, yes, we are going towards that direction. We will actually define what is a differential operator, in fact. We will mostly consider second order differential equation or differential operator because Laplacian operator is a second order, but we will also discuss first order. Yeah, yeah, sure. Thanks. Yeah, we are going there. Maybe tomorrow. Okay, good. Now, as I already have told, that we are interested in second derivative. Why we are interested in second derivative? Because Schrodinger equation, heat equation, wave equation, all are second derivative. So this is first derivative and we want second derivative. That means you act this operator twice, yeah, morally speaking. Okay, now we define it's a square. So t star, sorry, square, and this is on h20 ab to l2 ab, and as you expect, how should you define it? This is defined by this square u. So minus minus means plus and I square minus. So minus, maybe I also put this in color just for the first time that this comes from convention. Okay, so now okay, I haven't tell you what is this guy. So let me tell you. So it's again same, at boundary they vanishes, but um, let me write clearly. So u h2 ab such that f of a equals to 0, f of b. We have this condition before. And now it's a second order, as you were talking about first order ODE, second order ODE. So it's a second order ODE, we need two conditions, right? Its value and its a first derivative. So let's control its first derivative. Oh, sorry, I am mixing the notation. U. So first derivative u of a equals to 0, u of b. Okay. So now we learned how to define first derivative and second derivative as an unbounded operator on Hilbert space. Is it clear to all of you how to define? Because so far we were mostly interested with multiplication operator. Although I have shown you that if you use Fourier transform, then you can also describe differential operator in terms of multiplication operator. But the issue is that for Fourier transform, we need the isomorphism. And usually L2 is not the isomorphism. For Schwarz space, we had this isomorphism. And Schwarz space are not Hilbert space. So that's why this description is very nice, but this description is not say very useful in this context. So we define on the level of Hilbert space directly what is first and second derivative. So before I go ahead, is it clear? Because I'm pretty sure you know, you have used lots of time what is the derivative. But again, ask this question: what you know and what is presented here, why it has to be presented here, or how they are related, how they are not related, what was missing there. So I would say maybe I give 1-2 minutes, you contemplate a bit and come up with your questions. In the meantime, I just have some water. Okay, so any questions? Why the integration by parts is needed to define operator? It is not needed to define an operator because, as you have seen, this is the definition of this operator, and we haven't used integration by parts, right? But maybe you want to ask why then we are concerned with integration by parts. Just hold on, you will see. There is a reason why it has been introduced. But yeah, to define this operator, we do not need integration by parts. Any other questions, comments? Why we need this mumbo jumbo? Okay, it doesn't seem so. So let us going. So the plan, I mean, we are discussing self-adjoint operator is to discuss, analyze whether the first derivative and second derivative are self-adjoint, and when they are self-adjoint, when they are not. And as I am trying to stress repeatedly, it depends on domain. So we will change the domain. Okay, now we are using this domain, we will also change the domain. And we see that when it's or not. So for the time being, we are using this domain and we check using this domain. So to proceed, let us derive some small steps that we will be needing later. So first thing, maybe I write no. So the first property I want to write is that the image of this operator, then I take its perpendicular. Remember, we are in a Hilbert space, so we have a notion of angle and perpendicular. This is subset of C1. What is meant by C1? Okay, let me explain shortly. And we also have the operator T square. So you can, I think, it's natural to ask, what about the other? So yeah, right here. Image of T square. And then we take perpendicular. This is subset of C1 plus Cx. So we want to analyze the image of these operators. And now definitely I haven't defined what is this 1 and 2. So 1 means, maybe it's a different color. That means basically identity function. So a function gives 1. So it's not identity, it's a constant function which is 1. That's what I meant. And the later one, this one is the identity function. So if 2x goes to x, it's just a shorthand notation. For, of course, x in AB. Okay. Now let us prove this. Maybe I can use as a proposition, or maybe lemma. Let me write it as a lemma. Okay, so you know, by this orthogonality property of orthogonality, it is sufficient to prove that the other way around. That means C1 perpendicular is in the image of T, and C1 plus Cx perpendicular is in the image of T star. Okay, and how do we see that? So suppose H1 is in the C1 perpendicular, and H2 is C1 plus Cx perpendicular. Now we define functions on AB, the interval between AB, by G1 of x which is integration from a to x h1 of t dt, and g2 of x is integration from a to x, and then from a to t, so it's a repeated integration, h2 s ds, and then the other one dt. Okay. Now observe that h1, h2, they are L2. Why they are L2, I think, is fairly obvious, because since they are in this perpendicular, then if you just do square integration, this would be square integrable, right? And from there, so these are L2, we can simply conclude that K1 is on H1AB with, maybe I write here, K1 prime is, I mean, the derivative of H1 is K1. Yeah, it's a fundamental theorem of calculus. And K2, H2, AB, and the double derivative of, I mean, the double derivative of H different is this H2. So why H1 is just the definition. Yeah, you see this definition. It's just precisely this definition. Nothing else happening. And that's why we define the function this way, so that they are in this form. Okay, now remember we have other two spaces where here, something with boundary. So we want to check these conditions. So check. Check. So you just put K1 of A, and then I think it's fairly obvious. Sorry, I am using two different notation. Sorry, I mean G, 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 G. Okay. So this equals to 0, and so is G to A. Also, we check that G1B, what is that? This is nothing but H1 with 1 L2 inner product, and then this is of course 0. And similarly, G2 prime of B equals to H2 of 1. Perpendicularity gives 0. So what we have G2 prime of x, and now if I write from A to B, this equals to 0. Now come back to your question, why we are interested in integration by parts. Look at these formulas. Where? Here, okay, maybe we box it because these are useful. Okay, just observe this formula, and later we will also use this guy. So we box it also. Okay, so for the time being, just use this expression, and this gives us integration by parts above. Okay, so this gives us g2 of b equals to a to b into fundamental theorem of calculus g2 prime of dt. This is nothing but g2 prime with 1 inner product L2. And now comes, so we derive this integration by parts, and that tells that this is minus with this condition we have just checked is 2 double derivative with x L2. And then also this property we have seen here gives us minus h2 x L2, and we have seen that this is 0. So then what we have shown? We have shown that G1 is in the domain of T and G2 is in the domain of T square. And so T I G, sorry, T will be G1 equals to H1, and that's precisely the image of T, and T square minus G2 equals to H2, which is precisely the image of T square. Okay, so that proves our statement. Yes, here. So any question about, I mean, it's a simple derivation, but just a systematic, and you have to cook up the functional space in an appropriate way. So are there any questions? No? Is it too boring, too repetitive? Or you are lost? Okay, it doesn't seem to have any question right now. So this lemma might not be very interesting for the time being, because I mean, why we are interested image of this thing. But let's go something probably you will enjoy more. Our next lemma. So we want to discuss self-adjointness, and to discuss self-adjointness, we need the domain. And now we are here. So the next lemma tells us the domain of T star is nothing but this space HAB. Okay. And T star, sorry, of V equals to minus I times first derivative of V. Naturally, I think you are expecting the domain of T star, sorry, T square star and domain. And this is same as the domain of, I haven't proven the general properties, but you can look at the reference books, for instance. And this is given by H2AB. How this is defined? So T square star V minus the double derivative. Okay, so before proving it, I think this is the first instant where we are computing or observing the domain of an adjoint explicitly. Yeah, let's try to contemplate a bit. So let's go there. What we started with here. So that's the general definition of domain of an or adjoint of an operator. And now we have considered a very specific, perhaps one of the simplest non-trivial operator, first derivative, and then second derivative. And then question is, what is this domain? Okay. And now you see, this is precisely the domain. And once we have domain, we can define the operator, and that's how it is defined. So again, before proving, is this setup, or I mean, are you getting the main message or this language, like how we are describing and why we are describing? So is it clear, or is not, like why we are defining the domain in this way? I mean, why not we just take double derivative? Yeah, and then we take integration by parts that usually we do for adjoint. So is this clear? Is these things are clear? Okay, I do not see any question comment, so maybe I go through it and then we will discuss. But again, please, 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 if you have any question, interrupt me anytime. Okay. Okay, so we start with first we let's denote this is the domain. F is an element of domain of T. Okay. Since f of A equals to 0 equals to f of B. Okay, I'm mixing a lot, so let's not mix much. Let's put U, U, U. I mean, it doesn't matter, but I don't. Okay. Now, the integration by parts formula again. Integration by parts. So back to your question, why we need, and now you see why integration parts are coming up from the above, gives us T U V. So is it okay if I do not write L2 anymore? Because we are using L2 from now. I mean, if I change, then I wish I shall comment. Yeah, but I have to write L2 again and again. Okay, so the integration by parts formula, the first one, where is it? Here. So we see that due to boundary condition, this part vanishes. So we have boundary condition here, and this part vanishes. So that this equals to that. That's what I'm going to write. Minus I derivative of a u v. And this is nothing but u v. So I mean integration by parts again. So there should be a minus, and that minus kills a minus. Okay. Ah, sorry, this is plus. Okay. No, that's good. Because there was minus there. Okay. This is equals to u, and we take minus inside. Okay. Now, by definition of T star that written here, just above. Oh, sorry. Here. So definition of T star, it follows that V is definitely in the domain of T star, and T star V equals to minus I V prime. So is it clear? Like we had this very abstract definition before. Let me go there. Um, Here. And how we define it? We had first this equality in terms of inner product, and from this inner product we came here. We imitate the same thing now. So how we did it? So first we go with inner product, and to go with the inner product we need the integration by parts. Okay, because we have to add the operator from one side to another side, and how we do the integration by parts. So that's why. Yeah. Once we do this, then that's precisely what should come from the general definition, and that's what we have seen. Any question? Okay, probably not. So let me go. Okay, now go the next one. So let V is H2 is element of H2B. Then by definition of this space, def of this space, V and first derivative of V both are in H1AB, right? Because that's how these spaces were defined. Now, once something is on H1, then we can apply the result we have derived here and partly, okay, I mean, this is not right now required, but derived here. So we use it. Use what we have already, and twice, because it's a double derivative, so we have to use it twice. Maybe I write twice. Gives us gives t star v equals to minus I v prime. And then we from which okay, maybe I was too fast. Let's not go that fast. Hmm. Use this. Okay. Use this to V and then to again. So this equation again. T star V equals to minus V, sorry, 1 prime. We conclude that V is in the domain of T star square. Yes. And T star square V equals to, sorry, again, double derivative of V. So is it clear what we are doing and why? So it's a system, maybe I give you time. So what first we did, look, we need first this guy, right? I mean, to get T star square, we first need T star. How do we get? From general theory, you derive something like this. So we do this, and then, when you have this, you say, okay, so this is the guy that is defined T star, and there's the defined T star. Good. So that's gone, first step. Step two, we have the double derivative of this operator. That means we will act with this operator twice. Okay, then we take an element from its domain, and then the domain, just the way we define is that the first derivative are on h1. If the first derivative are on h1, then immediately what we derived for t star applied. So by this I mean what is in the upper part, okay, not literally this. Maybe it's also confusing. So use here. So what is everything in upper part? Okay, so now after this part, we know this guy, we know definition, we know the domain, we know the definition. Okay, and we see that the first derivative and also this v is satisfy the condition here in the domain, so that it is accepted to allow the result we derived here. Okay, then we apply this result to v once, and if you put v once, then you get this. And now you apply this again t star v, so then t star v will give you t star square v, and that's precisely the domain. And then you also get this expression. Okay. Unfortunately, I don't have time to finish it, and I don't also to rush because that's really crucial. Okay, so let's then continue the rest tomorrow. Maybe I use this few minutes to ask questions, comments. So I do understand now we are entering, or we have entered in hard analysis, not really hard, but the hardcore analysis. So who feel completely lost of this? Feel free to write me in chat that I am completely lost. Can you explain this part, or what can be useful to re-explain?